Hello, and welcome to this first video of a playlist about the preparation of alkylarenes. You may also check out my videos about fluoroalkylations and about the preparation of phenethylamines, which are somewhat related to this one. This first video is about the direct electrophilic alkylation of unsubstituted arenes with alkyl halides and alkyl esters or sulfonates. The second video is about alkylations with alkenes, and in part 3, alkylations with alcohols, aldehydes, and ketones will be discussed. Part 4 is about the alkylation of unsubstituted arenes with carbon-centered radicals and carbon nucleophiles. And in part 5, we'll have a look at the conversion of aryl halides and other substituted arenes into alkylarenes, for instance by nucleophilic aromatic substitution. Thus, most videos of this playlist are about the alkylation of arenes by substitution of hydrogen. There are many more ways to prepare alkylarenes. One important strategy, which I am not going to discuss in this playlist, is Friedel-Crafts acylation, followed by reduction. Aryl ketones can be reduced to alkanes by catalytic hydrogenation, with zinc and hydrochloric acid, or by strong heating with hydrazine and bases. Ketones can also be converted into tertiary alcohols by reaction with polar organometallics, and then reduced to alkanes. Electrophilic aminoalkylations with aminium salts won't be discussed either. You can find some examples of these in my videos about the preparation of amines. Other strategies that require a reduction and are not treated here are Heck and Sonogashira reactions, followed by hydrogenation, and reductive alkylations with ketones or aldehydes. In part 3 of this playlist, I'll show you some examples of alkylations with ketones. Aryl silanes, stannanes, and boranes are convenient but expensive intermediates for alkylarenes and will not be treated here. These intermediates are more nucleophilic than the corresponding unsubstituted arenes, but are often prepared from aryl halides. Direct alkylation of aryl halides is usually a more efficient strategy, as you'll see in the last video of this playlist. Many important products are alkylarenes, and some are manufactured on a huge scale. Ethylbenzene, for instance, is prepared by gas-phase acid-catalyzed ethylation of benzene with ethylene and is mainly dehydrogenated to styrene. It can also be used as solvent. It has a similar boiling point as xylene, but is easier to purify by distillation because there is only one isomer of ethylbenzene. Another important compound is bisphenol A, prepared from phenol and acetone. Acetone is a byproduct of the Hock synthesis of phenol, and the manufacture of bisphenol A thus consumes half of this byproduct. Bisphenol A is a monomer for the preparation of various polymers. Other alkylarenes include the anesthetic propofol, detergents, and liquid crystals for displays. The examples in this video are organized according to the electrophile, as shown here. Within each type of electrophile, I'll first show you examples of the alkylation of neutral arenes, then of phenols and anilines, then of heteroarenes, and finally of metallated arenes, including transition metal chelates. The alkylation of aromatic compounds by alkyl halides can proceed under acidic, neutral, or alkaline conditions. Under acidic conditions, carbocations are generated from the electrophile, which then alkylate the arene in a typical electrophilic aromatic substitution of hydrogen. Strong bases can deprotonate some arenes, and the resulting aryl anions can then react with alkyl halides to the alkylarene. Polyhaloarenes and arenes with a chelating group are particularly acidic. If the electrophile is more acidic than the arene, the alkylation can also proceed by nucleophilic addition of a carbanion to the arene, followed by elimination of the leaving group and aromatization. Such reactions are discussed in part 4 of this playlist. Substituents at the arene greatly impact the rate and regioselectivity of electrophilic substitutions. Here, various monosubstituted benzenes were alkylated with an allyl silane. Even simple alkyl groups enhance the rate of acid-catalyzed alkylation by a factor of 4 if compared to benzene, while chlorine or bromine decrease the rate by a factor of 10. Because the product is always more reactive than the starting material, Friedel-Crafts alkylations yield over-alkylated byproducts unless an excess of arene is used. Let's check some examples of alkylations with alkyl chlorides. Even with an excess of alkylating reagent, no exhaustive peralkylation occurred here. Paraxylene was heated with an excess of methyl chloride for 4 days, but mainly tetramethylbenzene resulted. Hexamethylbenzene can be obtained from phenol by methylation with methanol in the gas phase. One advantage of the use of alkyl halides as alkylating reagents instead of alcohols or ketones is that no water is liberated during the alkylation. Water will deactivate Lewis acids, and an excess of catalyst or high temperatures will then be required. Here, aluminum chloride was deactivated by the carboxyl group, and 1.7 equivalents were therefore necessary to bring about a complete conversion. Xylene served both as nucleophile and as solvent. In this example, aluminum chloride was formed from metallic aluminum, and the hydrogen chloride liberated during the reaction. Again, an excess of nucleophile was used. Allyl chlorides can yield indanes when treated with arenes under acidic conditions, as in this example. Here, the starting material isomerized during the reaction, a common side reaction of polyalkylarenes. Nitrobenzene is unreactive toward electrophiles and can only be alkylated, acylated, or halogenated under harsh conditions. Here, a low yield of chloromethylated nitrobenzene was obtained by heating the starting materials for 1 week in sulfuric acid. Benzoic acids can also be alkylated under such conditions. Bis-chloromethyl ether is a synthetic equivalent of formaldehyde and a dangerous carcinogen. Chloromethyl ethers are always formed in reactions involving formaldehyde and hydrogen chloride. Much more reactive than nitrobenzene are anilines and phenols. In this example, a dihydroquinoline was alkylated both at nitrogen and at carbon with bromochloropropane under slightly alkaline conditions in refluxing acetonitrile. Sometimes Friedel-Crafts alkylations succeed even in water. Benzylation of 2-acetylfuran with 2 equivalents of 4-fluorobenzyl chloride and aqueous zinc chloride yielded mainly 1 monobenzylated product. Aromatic benzylations can sometimes be catalyzed by palladium, as in this example. Here, a thiazole was benzylated in the presence of a dimethoxyphenyl group. The reaction conditions were slightly alkaline. In this example, a nitropyrazole underwent benzylation under conditions similar to those of the previous slide. No extensive benzylation of the solvent xylene occurred. I would classify this reaction more as a Heck-type addition of a benzyl palladium complex to the electron-deficient pyrazole than as an electrophilic benzylation. Some arenes form chelate complexes with transition metals, even without strong bases. These chelate intermediates are nucleophilic at the metal-bound carbon. Here, a pyridone was alkylated with octyl chloride via a nickel chelate. Alkyl bromides are more reactive than alkyl chlorides and generally preferred as reagents. I'll show you now some examples of alkylations with alkyl bromides. Under acidic conditions, as in this example, primary carbocations tend to rearrange to secondary cations by hydride migration, which can lead to product mixtures. Here, only half of the starting primary octyl bromide reacted without rearrangement. Occasionally, acid-catalyzed alkylations proceed with high regioselectivity. In this example, benzene was first alkylated 3 times with only a slight excess of ethyl bromide, and then, under more vigorous conditions, again 3 times with formaldehyde. Alkyl bromides that cannot rearrange, for instance, methyl, ethyl, or benzyl bromides, generally give higher yields of alkylated products. Here, brominated phenylacetone reacted with an excess of benzene to the expected diphenylacetone without alkylation of benzene by the ketone. Also in this example, the expected product resulted, despite the large number of other potential reaction pathways. The carboxyl group, for instance, remained unchanged, and cinnamic acid intermediates did not yield trityl acetic acid. This is an example of a palladium-catalyzed cyclization of bromobutylbenzene. The reaction proceeded under slightly alkaline conditions, and neither rearrangement nor elimination of the primary alkyl bromide occurred. A radical mechanism is therefore more likely than a mechanism involving carbocations or alkyl palladium complexes. Treatment of phenols or unprotected anilines with alkyl halides usually yields products alkylated at the heteroatom. The choice of solvent can affect the selectivity, as in this example. Here, sodium phenolate yielded 21% of 2-benzylphenol when the reaction was conducted in diethyl ether, where the sodium phenolate was not completely dissolved. In dimethoxyethane, however, only benzylphenyl ether was formed. Exclusive alkylation at carbon of phenols can be achieved with alkenes or alcohols as electrophiles, and there are some examples in the other videos of this playlist.
Here, aniline, protected as carbamate, was alkylated with a tertiary alkyl bromide under slightly acidic conditions. Only one isomer was formed in high yield. Unfortunately, this strategy is limited to electrophiles that form carbocations under mild conditions, such as tertiary alkyl halides or alcohols, and reactive benzylic or allylic electrophiles.
Lithiated arenes, or aryl magnesium compounds, are strong nucleophiles and bases and can sometimes be alkylated with alkyl halides. In addition to the examples in this video, there are some more in Part 5 of this playlist. Here, tetrafluorobenzene was metallated with butyl lithium at low temperature and then alkylated with a primary alkyl bromide. No arenes were formed, but a scale-up of this reaction is probably not possible due to the instability of the lithiated intermediate. Transition metal chelates are less reactive than polar organometallics, but can still be sufficiently nucleophilic to displace bromide from simple alkyl bromides. In this example, acetophenone, protected as imine, was converted into a cobalt chelate and alkylated with hexanyl bromide. The reaction was promoted by an excess of neopentyl magnesium bromide, which did neither react with the alkyl bromide nor the imine. A partial isomerization of the alkenyl group occurred. Here, pyridine was metallated and alkylated at position 2 with cyclohexyl bromide. Secondary alkyl bromides readily yield olefins when treated with bases, but here an acceptable yield of 2-cyclohexylpyridine could still be achieved despite the basic reaction conditions. With 3-methoxypyridine, the yield was even higher. Alkyl iodides are a bit more reactive than alkyl bromides, but more expensive and are only rarely used for large-scale preparations. Here, a lithiated dibromobenzene was ethylated with an excess of ethyl iodide at low temperature.
Again, because lithiated 2-haloarenes are thermally unstable and tend to fragment into arynes, this reaction will be difficult to scale up safely.
With the aid of norbornene as a reversible alkylating reagent, a number of quite remarkable arene alkylations have been reported. Here, for instance, an aryl iodide reacted with iodobutane and hexacyanoferrate to a 2-butyl benzonitrile. I've sketched here one possible mechanism. The outcome of such reactions will depend on the precise structure of the starting materials and will often be difficult to predict correctly. Nevertheless, this strategy can give quick access to products that would be difficult to prepare by other routes. Palladium chelates can also bring about electrophilic alkylations at electronically deactivated positions. In this example, a tyrosine derivative was methylated twice, not ortho, but meta to oxygen. This unexpected regioselectivity was brought about by the chelating picolyl amide. Here, protected phenylalanine was methylated with methyl iodide and palladium acetate, again with a norbornene as directing auxiliary. Unlike in the previous example, a clean meta-methylation occurred. Unfortunately, a large excess of silver acetate was required to reoxidize palladium. In the previous example with norbornene, no oxidant was required because the starting material was an aryl iodide. Here, however, the aryl palladium intermediate was formed by electrophilic palidation of an unsubstituted position with palladium-2, which must be regenerated from palladium-0 with an oxidant. In the previous example, the oxidant was air. In this example, palladium was also reoxidized with oxygen. The picolyl amide of a substituted benzylamine reacted with a primary alkyl iodide with high regioselectivity and without any rearrangement of the electrophile. Even electron-deficient arenes can be alkylated via palladium chelates. Here, a benzamide was orthoalkylated in high yield with a primary alkyl iodide. Alkyl fluorides are difficult to prepare, often toxic, and rarely used as alkylating reagents. In this example, fluorobenzene was alkylated with a secondary propargyl fluoride under acidic conditions, and mostly one of the possible isomers was formed. In Friedel-Crafts acylations, fluorobenzene also reacts at position 4 with high regioselectivity.
Alkyl fluorides are poor electrophiles, and nucleophilic substitutions of fluoride are slow and often yield olefins. Here, octyl fluoride was treated with an excess of phenylmagnesium chloride, and a mixture of the expected octyl benzene and octyl chloride resulted. Let's check some examples of alkylations with carboxylic and sulfonic esters. Simple aliphatic carboxylic esters are usually too unreactive to alkylate arenes, and in the presence of acids may even acylate nucleophiles. Secondary benzyl acetates, however, readily form benzylic carbocations and can be used to alkylate electron-rich arenes. Here, orthoxylene was alkylated with such a secondary benzyl acetate at room temperature. With 10% of iridium, palladium, or platinum chlorides, a high yield of diaryl ethane was attained. With protic acids and some other transition metal complexes, however, no reaction occurred, not even at 80 degrees Celsius. Mandelic acid phosphates reacted with an excess of benzene and 2 equivalents of triflic acid cleanly to diphenyl acetates. No acylation or methylation by the methoxycarbonyl group occurred. The large excess of benzene was required to prevent alkylation of the mandelic acid phenyl group and the phosphorus-bound phenoxy groups. Allylic electrophiles can convert arenes into allylarenes or indanes. In this example, mainly one allyl benzene was formed by allylic inversion, along with small amounts of isomers. In the presence of bases, phenylacetonitrile can be deprotonated and thus become nucleophilic at the ortho and para positions. Here, cesium fluoride was the base, and the para position was allylated with allyl acetate and catalytic palladium. Fluoroglucinol is a strong nucleophile and often reacts more like a cyclohexanone than a phenol. Treatment with prenyl acetate in boiling water led to alkylation at both the arene and oxygen. Butyrolactone can both alkylate or acylate nucleophiles. With just a slight excess of aluminum chloride, butyrolactone mostly alkylated benzene, as shown in the first equation on this slide. Under more vigorous conditions, the initially formed 4-phenylbutyric acid cyclized to tetralone. Just like we saw earlier with primary alkyl halides, also primary alkyl triflates tend to yield secondary carbocations under acidic conditions. Alkylation of benzene with butyl triflate and catalytic gold chloride and silver triflate gave mostly sec-butylbenzene. The more nucleophilic pentamethylbenzene, however, reacted under similar conditions mainly to the primary alkyl arene. This suggests that if an arene is sufficiently nucleophilic, alkylations with primary alkyl halides or sulfonates might proceed without formation of a carbocation, and thus without rearrangement. With the mesylate of methyl lactate and 2 equivalents of aluminum chloride, again no free carbocation was formed, and the alkylation of benzene proceeded with clean inversion of configuration. So what can go wrong? Let's have a look at some potential side reactions. Under acidic conditions, polyalkyl arenes readily isomerize and transfer alkyl groups to other molecules. Thus, acid-catalyzed Friedel-Crafts alkylations should be kept as short as possible to prevent such isomerizations. In this example, 4-tert-butyl-toluene was isomerized, but xylenes also react this way. Prolonged heating with acids can also lead to dehydrogenation and other unexpected reactions. Here, for instance, benzene was heated with catalytic aluminum chloride and hydrogen chloride.
Small amounts of biphenyl and ethylbenzene were formed, the latter from ethylene originating from the hydrogenation and fragmentation of benzene. Phenolates and anilines sometimes dearomatize when treated with electrophiles. In this example, alkylation of lithium dimethylphenolate with an excess of methyl iodide gave both the expected ether along with 18% of a non-aromatic cyclohexadienone. Oxidants can also activate halides and lead to halogenated arenes as byproducts. Here, gold trichloride catalysis led to a chlorinated benzene as the main product instead of the expected butyl arene. Carbocations can abstract hydride from positions where the new carbocation is well stabilized. Thus, the alkylation of benzene with terminal olefins can yield substituted tetralenes as byproducts by the mechanism sketched here. The key step is hydride abstraction by the protonated alkene from a benzylic position of the initial product. Hydride migration can then lead to a second intramolecular alkylation. Thus, strongly acidic conditions can also bring about oxidations. Then, of course, if an electrophile contains several electrophilic functional groups, it may react in a different way than expected. Nitriles, ketones, or esters are common electrophiles that can yield unexpected products. Chloroacetonitrile, for instance, can undergo Friedel-Crafts alkylations or acylations, depending on the conditions and arene chosen. In this example, naphthalene was alkylated by heating with chloroacetonitrile and catalytic ferric oxide and potassium bromide. When a 2-fluorotoluidine was treated with an excess of chloroacetonitrile, aluminum chloride, and boron trichloride, however, the main product was the orthoacylated aniline. Here is a selection of some further examples that you can also find in the description of this video, including examples of Claisen rearrangements. These are treated more thoroughly in the second video of this playlist, where alkylations with alkenes are discussed. Under the Posts tab of my channel, there is a PDF version of the slides. See you next time.